Alright guys, we're back. I told you there's a couple more things we got to talk about when it comes to exponential functions. One of the big ones is being able to compare them to linear functions. For some reason that's extremely important to tell a difference, so that's what we're going to do now. If I'm looking at this first example, again, just like the previous notes, I want to be able to tell which one's an exponential function, which one's a linear function. Hopefully by now you guys can see that one is clearly exponential and one is clearly linear. So, if you already know, you can pause the video, you can start doing this yourself, otherwise I'm going to keep going. If I'm looking at these two, -1, -1/4, -1/16, -1/64, that is definitely not increasing by a constant rate. If I look at the second one, -1, 2, 5, 8, plus 3, plus 3, plus 3, plus 3, this is clearly linear. It's going up by 3 each time. The slope is 3. If I'm looking up at this one, that's increasing by 3/4, then from there, I'm not even doing the math, guys. It's obviously not increasing by a constant rate of change. So, this has to be exponential. If you take a closer look, this is actually times 1/4. This is actually times 1/4, and this is actually times 1/4. But again, that's not a constant rate of change. Again, we don't multiply to get to the constant rate of change. We add or subtract. So again, this is being multiplied by 1/4. That has to be exponential. Okay? Easy. Second part, comparing exponential and linear functions. Now, one thing you guys may have to do is to compare linear and exponential functions given different intervals on a graph or just in terms of algebraic functions written out. So if I'm looking at the first one, I have two functions. I have 4x plus 2 and I have 2 times 3 to the x. It's clear that the exponential function is the one curving, and it's clear that the linear function is the one that's straight. I can see I have intersection points here and here, and those may come in handy later. But again, I want to be looking at these graphs, and I want to tell which one's larger where. So first one, when x is less than 0. So I want to know which function is larger when x is less than 0. That means I'm looking from here to here. So, given the first interval, if I'm looking at this exponential function is clearly larger or higher than the linear function is. When x is -1, that's roughly what? 2/3. And this is all the way down here, which is below 0. So again, given the height of these functions, and that's what we're talking about. We're talking about the height. The height of this function, the y values of this function are larger from here to here than the linear function is. So if I want to know which function is greater, clearly the exponential function is greater within this interval from -infinity to 0. Now let's look between 0 and 1. So I want to know which function is greater when our x is between 0 and 1. So from here to here. So if I'm looking from here to here, well, my exponential function is the curved line. If I look closely, this curved line is below the straight line. I get it's kind of close, but again, you can tell that this curved line, which goes here, is slightly lower than the straight line. Since the straight line is higher all the way through, since it's above the curved line, my linear function is greater in that sense. Now, I know I kind of cut off the graph, so you can't really see past 1, but they do increase. They both keep increasing. But I'm sure you can realize that this linear function will keep going straight, whereas this exponential function will curve higher and higher and higher, because again, we know the characteristics of exponential functions that once you get higher and higher, it increases faster and faster. So when x is past 1, when x is 2, when x is 3, when x is 4, when x is 5, our exponential function will be larger. So again, guys, we're looking at the height of the graph. We're looking at the range. We're looking to see how high are the graphs, which one is over the other. So again, those are the three answers there. Now I want to know which ones are higher, at 0 and at 1. So we're no longer talking about an interval. We are now talking about at certain points. If I look at x equals 0, I found 0 right here. Oh, that's an intersection point. So ask yourself, at the intersection point, what happens with these two graphs? They cross. Since they cross, they have to be equal. G of x is equal to f of x. And same concept for 1. 1 is also an intersection point. So that means g of x equals f of x. So in this case, they're equal. In these three cases, g of x was greater than f of x was greater than g of x. Wrote that slightly wrong. And in this case, g of x is greater than f of x. But here, the two are equal. So again, guys, if you're given a graph, it's incredibly easy just to look at the graph and figure out which one is larger. So just take your time. Make sure you understand what it means to be larger, what it means to be greater. Graphically, it means higher on the graph or over the other line. Algebraically, on the other hand, may be slightly more complicated. And by complicated, I really don't mean more difficult, I just mean more annoying, because it involves more work. There's no graph anymore. None whatsoever. I have two functions, y equals 4 times 2 to the x, and I have 3 halves x plus 5. I need to figure out which function is greater where. I have 3 intervals. Well, I lied. I have 2 intervals, and I have a point. I need to figure out which function is greater at these 3 selections. The only way you can do this is by substituting in. I could have done that here. I could have picked 0, plugged it in. I could have picked 1, plugged it in. I could have picked a number that fit these intervals and plugged it in, but why when I have a graph? Here, I don't have a graph, so I have to look at the interval, pick a number in that interval, and plug it in for both to see which one is larger. Let's do that. X is less than negative 3. Some number less than negative 3. I need a number less than negative 3. I can't pick negative 3 because it's not equal to. Has to be less than. I don't care which one you pick. Pick a somewhat nicer number. I'm going to pick negative 4. Why not? So I'm going to pick negative 4. For my linear function, y equals 3 halves x plus 5. It's y equals 3 halves. It's no longer x. It's negative 4. I'm going to substitute negative 4 in. Plus 5. I know that this is going to be negative 6 plus 5, which is negative 1. Y equals negative 1. If I do the same for my exponential function, y equals 4 times 2 to the negative 4th power. Oh, man. That means it's 4 over 2 to the 8th. Sorry, not 8th, 4th. Again, if I use exponent laws, guys, I don't have a calculator. I mean, I do have a calculator on my phone, but I'm too lazy to do that. I'm just going to do it. You know what? Just use your calculator. Don't worry about exponent laws. Plug those numbers in. Just make sure you include the negative with it, or else you're going to get something totally wrong. So if I do 2 raised to the negative 4th power, do I not have a negative sign on my phone? I don't have a negative sign on my phone. Why is there no negative sign on my phone? Are you kidding me right now? Bootlegged androids. Well, I guess I can't do it on my phone. So I'm going to go with this route. Type this in the calculator, plug it in, you'll figure out which number is larger. I'm going to do it this way. 2 to the 4th is 16. Exponent laws means whatever is raised to a negative power gets put into the not the denominator, but it flips over the line. So again, it's going to be 4 over 16, which we know is 1/4, which we know is 0.25. That's negative 1, by the way. My bad. So negative 1 versus 1/4. 1/4 wins. 1/4 is larger than negative 1. That means the exponential is larger for this interval. Let's use negative 3 now. So if I use negative 3, y equals 3 over 2 times negative 3 plus 5, which is negative 9 halves. So it's negative 4.5. Negative 4.5 plus 5 is 0.5, or 1/2. Okay, that's my linear. If I do exponential now, I'm going to do y equals 4 times 2 to the negative third power. Again, just like here, this also means 4 over 2 cubed, which also means 4 over 8, because that's 2 times 2 times 2, which is 1/2. 1/2 equals 1/2. These two are equal. At this intersection point, these are equal. And typically, guys, if they ask you to figure out which one is larger at an intersection point, they're most likely going to be an intersection point, and it's going to be equal. Okay? It doesn't say it's going to be an intersection point, but you can kind of just intuitively tell it's going to be an intersection point. It's going to be equal. But test your math anyways. You see they're both 1/2. Now, I want to go from -3 to 0. I need some number between -3 and 0. I'm not going to make this difficult. I'm going to pick -1. So I'm going to have y equals 3/2 times -1 plus 5. So this is -3/2 now, which we know -3/2 is -1.5. So this is going to be 3.5, not 35, 3.5. Last one, y equals 4 to raised to the -1 power. That just means 4 over 2, which is 2. In this case, the linear is larger because, again, 3.5 is larger than 2. I'm showing you the math, guys. You can just plug this in your calculator and do it as well. Just don't forget the negative sign. Make sure you use the caret button when you do it. And you would find out it's 2 anyways. But again, as you see with the math in front of you, the linear function is larger in this interval. I don't have to check every number in the interval. If one number works, that means it's always going to work. I'm sure you can figure out what happens at 0, then past 0. Just based on our last example as well. But again, you can see within this range, it's linear. So whenever you guys are given two functions without a graph accompanying it, you have to do it algebraically. You have to pick a number in the interval and then plug that number in. And again, make sure there's no equal sign underneath the less than, greater than signs. So you can't pick -3 and 0 here. You can't pick -3 here. It has to be a number in the interval. So that's what happens with the growth and not growth. That's what happens when you're comparing linear and exponential functions. So guys, that's that. On the back of the second side of notes, I'm going to do that in a different video. If you have any questions on this, let me know. Otherwise, hope you guys understood everything, and I'll see you guys later.